Okay, so welcome everybody to our official start of Big Data for today. I have a few quick announcements for us, and then we will get into today's material. So first I'm going to, let's see, I just made an announcement on GitHub about this Friday. I have a conflict with our the 10 a.m. lab time that we'd created. So if you, so that time's not going to happen this Friday. If you would like to still have a lab session this week, I posted an issue on GitHub. Just reply to that issue with a time that you'd suggest that we do it at, and if there's a consensus around the time, then we'll make that our lab time for this week. This should be the only week that we have or that I have a conflict like this. This was something that was pre-scheduled before the semester started, but should be, I won't schedule anything else from here on out. Are there any questions about anything from last week? Yeah, I looked at, most of you have the homeworks in the lab submitted, although everybody who did that got full credit on both of those, so good job. But are there any questions about anything from last week? Okay, then I'm going to share my screen and we'll get started. Yeah, so first of all, this is that announcement that I just mentioned. Just reply to this issue if you have a suggested time for lab. But let's go over to our week 1 right here. And today, or this week, we're going to start talking about a system called Docker, which is used for well, it's used for a lot of things, but it's sort of more of a software engineering tool than a strictly data science or big data tool. And today what we're going to talk about is some of the background from operating systems that we need to know in order to fully understand what Docker is doing. And in particular, today we're going to talk a lot about parallel programming stuff. Yeah, we're going to talk about a lot of stuff really quickly in like 5 minutes right here. And this is all of the hardest things from an operating systems course that's just compressed down right here. So don't feel like you have to fully understand all of this stuff. This is just going to be a background so that you have a rough idea of what this concept of a process is in Unix systems. And we'll see how to use those in both Python and the terminal in Bash. And this week, you'll notice that there's no homework posted up here, no repository homework. And that's because this week, your homework is going to be this Twitter homework that's already posted. And so we'll talk about that as well. And this is very closely related to what we're talking about today in terms of parallel processing and these operating systems concepts. But then we have a shorter lab posted down here as well, which is the purpose of the lab is just to help you get Docker installed and running on the Lambda server. Okay, so for parallel programming, there's really 2 basic techniques that people use to do this, threads and processes. And the main thing to understand about the difference between them is that threads are lightweight, so there's minimal overhead, whereas processes are heavyweight. And by heavyweight, I mean that they take about 10 megabytes of unavoidable overhead. So threads, no extra memory required in the kernel. In order to do threads, everything is shared between different threads in the same program. Processes, every process you have takes up an extra 10 megabytes of memory on your system. So yeah, these days memory is cheap, so people don't really care necessarily too much about processes using this extra memory. But 20 years ago, this was a huge deal. And so people really, a long time ago, were very much using threads much more than processes. Another potential advantage of threads is that every thread uses the same memory, so it's relatively easy to do communication between threads, whereas processes, there's no shared memory. The only way to communicate with processes is by reading and writing to files. One of the things that'll come up later in this course when we start talking about different database systems is some databases tend to be a little bit more secure than others. And that's because some databases use threads and some databases use processes. And threads tend to be a little bit harder to work with. There's lots of sort of tricky ways to get bugs in threads. And that's because they have this shared memory. If there's a problem in one thread, it's going to corrupt the other threads as well. In Python, though, there's something called a global interpreter lock. You'll hear Python programmers talk about this lock all the time. And this, like the main takeaway from this is that it is impossible to use threads in Python for parallel programming. So if that's the one thing that you remember from today, it's that threads in Python, you can't do it. It's just impossible. And so we're only going to be talking about processes. And so for us, for our purposes, the difference between threads and processes is just like a theoretical thing that we don't really care about. Yeah, it's really quick overview of the difference between threads and processes. What we're going to talk about next is actually using processes in Python. We'll see these two, this function right here, os.fork, and this multiprocessing library. But before we do that, are there any quick high-level questions about the difference between threads and processes? Okay, yeah, so again, just the takeaway is that you'll hear people talk about threads in other programming languages. Python, you can't use threads, so it's all about processes. So over here, I'm going to switch to a terminal. There we go. And on this terminal, I have, again, two windows open. This is how I'm going to do most of the coding that I'm going to do in class, and it's how I do all of my coding with two windows open. Typically on the left-hand window, I'll use Vim to edit a file, and then on the right-hand window, I will actually type in commands. So right now, I'm in, or the way I typically structure my home folder is that I have a project folder where I keep all of my projects, class repositories being one of them. And now I'm inside of my CS143 and then inside of the week one folder. So right now, if I type ls, here's the just the README file and the image file that you find on the GitHub repository. And what we're going to do, first of all, is create a file fork.py. And let's go ahead and save that file. Oops, lowercase w. And now over here in the same folder, fork, readme, and so now there's three files this fork just recently created. Because this, this prompt is taking up so much space, I wouldn't normally do this when I'm working by myself. I'd have the font slightly smaller. But what I'm going to do again is do the export ps1 equals and then $ space like this, so that my prompt is a little bit smaller and it'll be easier for all the commands to stay on one line and easier to follow along, seeing what's going on. So just real quick, make sure that things are working. Print hello, save that. Let's move it down so we can see it. And then over here, do Python 3 and then fork.py, and it prints hello. So on the Lambda server, anytime you have a Python file, this is sort of the standard, simple way to run it. What we're going to do is illustrate how this fork command works in order to do parallel processing. But before I get into that, are there any questions just on the setup that I have here?
Yeah, how are you getting the two windows like side by side?
That's a good
Like,
question. Yeah, so what I have is just, let's see, so there's sort of like two standard ways that people do this. The way I do it is I just open up two terminal windows on my operating system and connect both of them separately via SSH into the Lambda server. And then I use what's called a window manager called Xmonad that automatically tiles things for me so that it's fills up my whole screen and puts them nicely side by side. Other people who don't want to make, say, two separate SSH connections, say if you're on like PuTTY and Windows, that's a little bit cumbersome. There's a program called Screen that you can run on your terminal. It's SCREEN. It's a little bit complicated to set up with all the options, but this lets you divide up a single terminal window into multiple terminal windows. And yeah, this sort of side-by-side environment's really common with Screen as well. Yeah, so the short answer is that it's going to depend on your own system, how you get that set up. That's a good question. Any other questions before we keep going? Okay, so here, let's see, when I'm running this program, so I did Python 3 and then the name of this file in order to run this file. What we're going to talk about first, though, is how we can let the operating system know that this is a Python file and we don't need to type Python 3 here in front of the file name in order for it to run. And so if we just tried, for example, fork.py like this, it'll say command not found. And it'll turn out there's two reasons for that. But the first reason is that this fork.py file is not what we call executable. And in Windows systems, and a little bit in Mac systems, the way the computer knows like what the file type is or what a file is supposed to do, whether it's executable or not executable, is it uses the extension of this file, this .py right here. But on Unix systems, the extensions actually mean nothing. So Mac, 20 years ago, Mac was not a Unix system. About like 10 to 15 years ago, the Mac OS switched over to being Unix. And so everything on the terminal in Mac behaves the same way, but there's still a few GUI applications that depend on this file extension. But for the most part, Mac will use this system that we're about to talk about. So in order to see what type of file this is, you use the ls and then the -l command. And the -l again gives us verbose information. And this information over here is what's called the permissions on the file. And here we see a bunch of R's and W's, and these R's and W's stand for read and write permission. So we have read and write permission to this file, which makes sense because we just created this file, and so we are the owners of this file. Currently logged in as user test, so this is the, you can see that if you type who am I anytime in the terminal, it'll tell you who you're logged in as. And so this column right here is who is the actual owner of this file. Or this column right here is who is the owner of this file. These permissions over here are divided up into sort of three groups of columns. So these last three over here are everybody has these permissions. So everybody's allowed to read, this R standing for read, but there's no W in these last three columns, so not everybody's allowed to write. These three right here are what are called the group. All of you are part of a group called students. And so if somebody is in that same group as you, then they have these permissions to this file right here. And then this last one right here is what we as the user are allowed to do to it, and or the owner of the file, what we're allowed to do to it. And what we want to do in order to be able to execute this file is we have to add execute permissions. And so there's a command chmod, which lets you adjust what these permissions over here are on any given file. And there's a lot of different syntaxes for this, but the easiest one is you do a I'll show it like this, U plus X. So U standing for user, but I could say G for group or A for all. The fact that I'm using U means it's going to adjust these 3 spots right here. If I did G, it would adjust these 3 spots right here. And if I did A, it would adjust these 3 spots right here. And then there's an X for execute, an R for read, and a W for write. So here I say chmod A plus W fork.py, and then ls-l, and we can see that if you look at the difference between on fork.py, here's the permissions beforehand, here's the permissions afterwards. So now everybody has write access as well. Usually you don't want to do that. You don't want to give everybody write access. So I'm going to take that away by saying A minus W. And now I've taken write access away from everybody, including myself. In order to give myself write access back, U plus W. And now I have write access back right here, but it's still only read access for everybody else. The particular permission that we care about though for right now is the execute permission. So U plus X, X stands for execute. Now I can execute this file directly. Do ls-l again. And this X right here means that I can execute it. And you'll notice that the color of the file also changed to green. If you have downloaded my settings for Bash, then anytime a program is executable, it'll be green like this. So real quick summary of these permission systems, but are there any questions about that?
Quick question. Who has permission to change these permissions? Is it just the owner?
It's a great question. So the owner has permission to change these permissions and the system administrator. On Unix systems, the system administrator account is traditionally called root, R-O-O-T. And so I have root access on this system, so I would be able to change your permissions to whatever I wanted. I would be able to read your files, even if you say they don't have read permissions. But otherwise, it's only the owner of the file, whatever person is right here. It's a good question. Any other questions so far? Okay, so now let's try doing the fork.py like this. And you'll see that it still gets this command not found. And what this leads us to the second part about how you get these programs to be able to execute. And that's that you have to actually tell the computer where the program is located that you want to run. So in this case, this file is located in the current directory that I'm in. And so if you remember, the dot by itself, the period by itself references the current folder that you're in. And so if I did ./fork.py, that would try to run this program like this. And here you'll see that it's actually giving us these syntax errors. So it's running it, but it's not running it correctly. And we know that there's not actually any Python errors, because if I did Python 3 like this, and then fork.py, it actually ran correctly. So the question is, why is it giving us these errors here? And the answer is that we haven't yet told it like what programming language we're using in this fork.py file. We know that it's Python because it ends in this .py extension here, but the computer doesn't care about file extensions at all on Unix systems. So we have to specifically tell it where that it's a Python file. And the way that we do that is on the very first line, we add what's called the shebang to the file. So the hashtag exclamation point often pronounced as bang, called the shebang together, needs to specify exactly what program should be run in order to run this file. We want to use the Python 3 program like this. And so we need to first figure out where on the computer is Python 3 located. There's a command called which which tells us exactly where's the location on your computer for any executable. So if I did which ls, that's located in /bin/ls, but which python3/user/bin/python3. There's a handful of different folders on your computer where these executables can be located. And so that's why this which command is useful. It tells you exactly where it's located. So I'll copy and paste this up here. And hopefully you all can still see. Oops. Oh, I can move that around. That's useful. This is just the path to the program that will execute this file. So we'll save that. And now if I come down here and do /fork.py, it knows to run it with Python and it runs it correctly. So it's very common in Unix systems to have Python installed in this particular location. And so it's very common for Python scripts to start with this first line. Are there any questions about that? Okay. So now that we've talked a little bit about the permissions issue and how to get these programs running a little bit more natively than just typing in Python manually each time, next we can talk about this fork function and how it lets us run things in parallel. And this fork function is, it's a particularly confusing function and not something that you'll want to call directly, hardly ever, but it'll be useful to illustrate here what exactly it's doing so that later on, when you're not calling it directly, but you're using other things, you can understand sort of under the hood what's happening. So in Python, the fork function is located in the OS module. The OS module is built into Python. And it's the module for interacting directly with the system kernel. In Python, most libraries are system agnostic. Most libraries work the same for Windows, Mac, Linux, etc. But the OS module is something that can sometimes behave differently depending on which operating system you're on. This fork function is one of those functions that can behave differently depending on which operating system you're on. We won't talk about those differences in this class, but it's just useful to know that if you're in this OS module, then you're sort of playing with fire in terms of the portability of your code and the ability for it to run on other computers. So in order to actually use the fork function, you do something like os.fork. And I'm going to run this code and we'll see what's going to happen. I'm just going to run it here, and you'll see that this hello actually gets printed out twice, whereas before, when I did not do os.fork, hello only got printed out once. So why is that? The answer is that fork actually returns twice, whereas every other function in Python and in most programming languages only returns once. And when it does this, what it does is when you call os.fork, it creates a copy of your program in memory. And then that copy also returns separately. That copy is called the child process, and it continues execution from this location, in this case line 14, continues execution just like the original. execution, just like the original. So when you call os.fork, copies your program, then both programs start running, and those two programs will run in parallel. And that's why, because there were two programs sort of in memory, two programs running, this hello printed out twice down here. There's a return value for os.fork, and it returns something different depending on whether you're the child or the parent. So if n equals 0, print we're the child. And if n is greater than 0, print we're the parent. So if we run this again, we'll see once it's printing we're the child, once it's printing we're the parent. Let's see, when we run, if you remember, there's the ps command. The ps prints information about processes. And so this, every time you call fork, it's creating a new process. So it will create a new entry that PS will be able to find. So this is a little bit confusing because right now on the right-hand side, remember this window is in a separate SSH login. So we don't have direct access to these programs that are running over on the left. And we have to do the ps-ef pipe grep. And here we'll search for user test to see all of the programs that are being run by user test. And now we're going to look for these left-hand programs that are being run. So I'm going to, down here, while true, while true, continue. So we'll have an infinite loop over here, print out we're the child, we're the parent, and then infinite loop, so neither program is going to actually stop. And I'll first run this, whoops, while true, and I'm actually going to, let's see, so right now I'm in Vim on the left-hand side. I press Control-Z to send Vim to the background. I'm going to run my fork.py file on the left-hand screen. So we're the parent, we're the child, they're both running in the background over here. And now on the right-hand side, I'm going to do the ps-ef and make it a little bit bigger. We can see two copies now of this fork.py that are running right here. And they have two separate process IDs. So if I want to communicate with them, I need to, I communicate with them separately using their process IDs. The main tool that we'll be using in this class for communication is the kill command, which lets you kill processes. And so we'll first kill this 50041. And now if we run that again, we can see that this one right here has been killed. This one here is still running. And so let's kill that one next, like this. And once they both over here quit, Control went back to the terminal and running ps-ef over here, it no longer appears up anywhere over here. Are there any questions about that?
So how many times can we fork something? Can we do it more than once?
Yeah, this is a great question. And so the question is, how many times can you fork something? And the answer is that it's, this is one of the sort of security settings that is set on your account. We could imagine, for example, this really evil code. It's so evil that I'm not even gonna type it out as regular code. But if we do something like while true in an infinite loop doing os.fork, then this is called what's called a fork bomb. And this is going to just infinitely create all of these forks and processes on on your system. And in your case, as students on the Lambda server, you are limited to 1,000 processes running at any one time. So this will instantly use up all of your process resources. Fork bombs are particularly dangerous because they're really, really hard to get rid of. Because as soon as I were to, or as soon as you were to say, kill one of these, because it's inside of an infinite loop, it's just going to instantly create another one again. And so generally, if you're, as a user, you run a fork bomb like this, you won't be able to do anything on the computer until a system administrator comes in and fixes it for you. So you do not want to run something like this. The reason why you're limited to only 1,000 processes is because, remember, every process takes up about 10 megabytes of system memory. And so if you did not have that limit, and you were to run something like this, then you would instantly use up all the memory on the server, and the server would crash and nobody would be able to do anything. So because you have that limit, the server does not crash, but you still are not able to log into your account until, or accomplish any tasks until I would come in and delete all of those forks for you. On the Lambda server, there are 80 CPUs, and so you cannot effectively do more parallelism than 80 processes running at once. And so generally when I'm doing something in parallel, I create 80 processes, one for each CPU. Good question. Any other questions so far? Okay. So inside of Python, there's another library called multiprocessing, which sort of abstracts this forking away from you so that you don't have to deal directly with this fork system call, and you don't have to worry about accidentally creating one of these fork bombs, for example. And this link to the library is right here. You can reference it if you want to, but we're not going to talk about it in detail in this class. Instead, in this class, what we're going to do is we're going to be using bash directly for all of our parallel processing needs. That in Python, it's not very great for manipulating multiple processes, and it's very easy to create like really, really bad bugs that are hard to catch. And a lot of those bugs are not possible in bash. So that's one of the reasons why I prefer bash for this source of parallel programming. To illustrate what those bugs can look like, let's say before calling fork right here, I was to create a very big variable up here. So we'll create a list, or create variable XS list of range of 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. So what this syntax is doing, this is a list containing all the numbers from 1 to 1 billion. So in Python, each number takes up about 8 bytes. A billion is approximately a giga, so this is approximately 8 gigabytes right here of memory. The Lambda server has 256 gigabytes of memory, so it's not a problem for it at all. And but it's still going to be relatively inefficient. When you do this os.fork, because it has to copy all of the memory that's inside of your program, it has to duplicate all of these big variables like this. And it's really easy to accidentally duplicate these variables into code that it doesn't need it. And so you get what's called memory leaks, where your code is using up a lot more memory than it actually needs. So for this reason, among many others, we're not going to directly call this fork function from Python in this class. Instead, what we're going to do is we're going to do the forking from within bash. So I'm going to create a new file. So in Vim, in order to create a new window, in order to edit another file, you use the command :tab-E. The E stands for edit, so it's like a new editor tab. And we'll call this bash fork, and we'll call this .sh. So it's traditional for bash scripts, anything that's running inside of anything that's just a sequence of commands that you type into the terminal over here, that would be what we call a bash script, and it's traditional for that to end in .sh. So over here we saw before that there's this echo command that we can use to print something out, so echo hello world, and if I were to, in this bash fork.sh, type echo hello world like this, and then over here on the right hand side I can type bash fork, and it'll print out the hello world. Or I can again do the chmod user plus x bash fork.sh. So now it has executable permissions, and you'll notice that if I do bash fork like this, it prints out hello world just fine. So when there's no shebang at the top of the file, the Unix systems automatically interpret that as it's a shell script, something that's just shell commands that are to be executed over and over again. But if it's written in any other language, you have to have this shebang at the top of the file. Even though it's not required to have a shebang for a shell script, it's very, very common for people to do that. So let's find where is bash located, /bin/bash/bin/bash right here. And now what we're going to want is another Python file. We'll call this file longrunning.py, and let's do /user/bin/python3 up here, and import time and print starting, and then time.sleep 10 print stopping. So this long running file is just going to print this, wait 10 seconds, and then print stopping. And so we can do Python 3, long running, and printing starting, waiting a little bit. And there we go, stopping. And now I'm going to change this, user plus x longrunning.py. And now inside of my bash fork over here, we print hello world, and now I can do longrunning.py, and we can do it a couple of times, and each time it will sort of first it printed out hello world, executed this line, then it went on to this one, starting, it'll take 10 seconds, and then it'll print stopping. Oh, whoops, I did the wrong file. I did long running. I wanted to do, there we go, bash fork, printed hello world, starting. It'll take 10 seconds, it'll print stopping, and then that was for this first one right here. And then we'll want it to keep going, and it'll keep going one after the other down the list. I don't want to wait for all this to finish, so I'm just going to press Control-C on the terminal on the right-hand side, and you'll notice that it stopped one of these programs. It stopped the long running that was running right here, but it didn't actually stop the bash fork. I have to keep pressing Control-C for all of these until it does that. And each one of these was running in sequence. They were not running in parallel. In bash, in order to make something run in parallel, you put the ampersand after the end of your command. In bash, the ampersand, what it's actually doing is it's calls the fork syscall. So a syscall is anything that's interacting with the kernel. In Python, anything in the OS module is a syscall. Sys standing for system, and calls the fork syscall so that all of these things will end up running in parallel. And if we save that and rerun this down here, then you can see it printed out 4 of these startings, and it'll wait 10 seconds, and then it'll print out 4 of the stoppings all at the same time. You notice that it's not printing the $sign right here. It's not printing my prompt. And this is something that's potentially very confusing. And the reason for that is because it's already printed it up here. That because all of these things were told to run in parallel, they all immediately ran, and control went immediately back to the terminal as soon as this one finished. And so that's why the $sign was printed up here. I could have been typing in commands at any point after starting this process. I can type ls, and it's still just like I'm in a normal terminal session, except this is running in the background, and so those will print at some point. Even though this word stopping looks like it's a command that might be executed after this $sign right here, because it was the output of a program and not something that I actually typed in on the keyboard, it's not actually a command, and if I hit enter, nothing runs. Are there any questions about any of that? Okay. So, yeah.
Question.
Go ahead, please.
So is fork also used for prior programming, or we just use bash? I'm trying to. I think I'm still struggling to understand why we need fork.
For the purposes of this class, what you just need to know is that it's possible to do fork from within Python. It's possible to do parallel programming within Python, but we're not going to do it because there's too many bad things that can happen, and we're just going to do it from within bash.
Okay, perfect. Thanks.
Yeah, so that sort of begs the question of like, why even bring it up at all? And the real answer for that is to, for the data science students here, just to get you to some exposure of what are the things that you would be covering if you were, say, taking a computer science major and some of the upper division computer science courses. And this fork system call is sort of like the main thing that you would talk about in an operating systems course. So in an OS course for CS majors, fork is like the key thing that the entire course is built around. Understanding exactly what that fork is doing and how do you effectively program with that fork command. For our purposes, we just assume that that's been taken care of us. We don't care about any of those details. And we're just not going to call it directly in our programming languages so that we avoid all of those problems. You will, in a lot of data science applications, see people like using these parallel programming from within Python. Typically, they won't do it directly with that fork call. They'll do it with the multiprocessing library, which is a little bit easier to use, but it's still very, very easy to write very buggy code and not know that you're writing code, or not know that your code is very buggy. So I would strongly suggest running away from that code as fast as you can if you ever see it. See, good question. Any other questions so far?
The bash script isn't going to get rid of the memory problem, right? Like it's still going to use up that as much memory as doing it in Python would do.
Exactly, that's a great question. So yeah, that's one of the other key takeaways, is that it doesn't matter where you're calling this fork from, it still takes up the same amount of memory. It still has to do the same thing of duplicating your entire process in memory. And it's still going to contribute to the limit of the amount of processes that you're allowed to run. So you all are allowed to run just 1,000 processes. And so it doesn't matter whether you create those from bash or create them from fork inside of Python or from some other method, that it's still the same resources being taken up.
And is there any way to, like, this may not be a good question, but is there any way to sort of have memory that you promise is unmutable, and have that be shared across processes, or no?
Good question. Some operating systems allow that, some don't. As far as I know, in Linux, if you want even like read-only memory between processes, it has to be done through files.
Okay, thank you.
Yeah, if you're sharing memory directly between parallel processing things, then that's threads, and that's can't be done in Python at all. So that's another takeaway from this discussion, is that these threads can't be done in Python because of this global interpreter lock. And so because of that and the complexities of using the fork function, it's basically just not worth doing parallel stuff in Python at all, and just do it in Bash. Yeah, since we're over here on this page, one of the things that this parallel processing can lead to is a very difficult class of bugs called Heisenbugs. So Heisen coming from Heisenberg's uncertainty principle, that when you look into it, try to observe the phenomenon, it changes. And so it makes it very difficult to debug it. And here's some two examples of a simple Heisenbug and a really complicated one. This one down here is very famous, so it's just a short read. I recommend you read it and be amazed at the person's debugging prowess. Okay, so yeah, it's a quick overview of forking and processes in Python. And so now we're going to change gears slightly to talk about this mapreduce paradigm for parallel computing. Mapreduce is a way for making these, basically formatting your code, structuring your code in a way so that it becomes relatively easy to debug and not have some of these problems that we were talking about before. And so as long as you sort of stick to this mapreduce path, then you can pretty much ignore everything that we've talked about up until this point and just know that the reason you're doing mapreduce is because everything else is really complicated. And so to talk about mapreduce, we're going to go back to this Twitter homework right here. And this Twitter homework is essentially a homework about the mapreduce system. So first I'm going to scroll down to this image right here. And this image is sort of the summary of what mapreduce is all about. So you have some big data set. So in our case, the data set that you'll be working with is the set of all tweets that were sent in 2020 that have GPS coordinates associated with them. So there are about 500 million tweets sent every day. In total, about 2% of those have GPS coordinates associated with them. And so if you do work out the math, that's about 1.1 billion tweets that are in this data set that you're going to analyze. This may sound like a big number, and to some people, this would be like in the realm of big data. But this is going to be relatively straightforward to actually handle on a single computer. And so this is something that I would still consider in the small data realm. If you were to think about like the total amount of disk space that these tweets use up, it's about a little bit over 1 terabyte of disk space. Yeah, so you have this, so a terabyte's still pretty big, so I'll still call it a big data set. And you have to partition it into smaller data sets somehow. So we saw before in the lab that the data is, there we go, partitioned into all of these different zip files, where one zip file represents 1 day's worth of tweets. And so that's the partitioning step, which I've already done for you. Generally, the partitioning is, for any data sets, pretty straightforward to do. There's usually some sort of like logical timestamp or something like that to partition on. But even if there's not something like that, you can just do a random partition. This step usually is totally inconsequential. The map step is the step where most of the computation is going to happen. And in the map step, we have to compute something from one of these smaller data sets. So in this project, what we're computing is we're trying to count how many times coronavirus is mentioned in a whole bunch of different languages and in a whole bunch of different countries. So in order to talk about exactly what's going on, we're going to switch again to the terminal and look at some code. So here, this Twitter coronavirus repository is what we're going to look at. And so I'm going to copy that URL right here. Maybe a quick side note for Git. Anytime you see something inside of a Git repository that ends in one of these sort of hash numbers like this is called a submodule inside of Git. And it's basically a Git repository inside of a Git repository. So this submodule right here, you notice that if I go back to my terminal, so let's clear this, find our current location. I'm going to go cd ... and then cd homework_Twitter ls. So this location that I'm currently at, this location right here, is the same as this location right here. I have the Twitter coronavirus readme mapreduce, but inside of my Git repository right here, if I go inside of Twitter coronavirus and type ls, it looks like there's nothing there. And the reason for that, again, is because this is a Git submodule, like a Git repository inside of a Git repository. And in order to conserve disk space, Git does not load up these submodules inside of each other. Instead, if you want to get access to it, you have to, let's go out one more. So now I'm in my generic project folder, and I have to reclone this file, or actually clone it for the first time. That's not the right URL. Here we go. I have to actually clone this separately. So even though it looks like the class Git repository already contained this, I still had to clone it separately. And now I can go inside of Twitter coronavirus, and I have access to everything here. So we said that the partitioning step has already been done for you. And then, so the next step is this map step. And I have this Python file right here, which is sort of a framework for you to work with when doing this map step. You'll have to add a little bit of code to it yourself, but we'll talk about that later. First, we're going to talk about just like what is it doing and how do you run it. So you'll notice that these files are not green. They do not have execute permission. No X's inside of these permissions. So I'm going to do chmod user +x on source/map.py. And now I can just run this map.py file. And inside of the instructions for the homework, I have an example command under this background tasks. So this is the command that I'll run right here. Each one of these map.py files, or the map.py file itself, it takes a single parameter, which is a single one of these Twitter files. And there we go. Source/map.py, and we'll run that and make that a little bit bigger so you can see the whole thing. And it'll take, it takes about 5 minutes to process just one of these files by itself. So let this run in the background for a little bit. And you can see that for sort of debugging purposes, I have it printing out every hour, just after it's finished the tweets for an hour, gives me an update about how long it's taking. And so you can see it takes about 13 seconds to process 1 hour. And so that's where I got the 5 minutes of 13 seconds times 24 hours. So while that's running over on the right-hand side, I'm gonna switch out of here and we'll take a look inside of what this file actually looks like. And with Vim, you can directly open up zip files. So Vim, and then open up that zip file. And what it shows you is all of the different files contained in the zip file. And now if I wanted to look at the contents of, say, this first one, I press enter. It takes a second to decompress all of that. And now here's the contents of the file. The way this file is structured is that it is it's what's called a JSON file. So if you look at this, it looks like a Python dictionary that's just formatted really ugly. And so this curly brace starts the dictionary and then created at, and here's the timestamp that it was created at. And then here we go, here's the text, and here's the actual contents of this particular tweet. Anytime you see this \U, that stands for Unicode, and so Unicode is sort of a standard system for encoding non-English characters, and so this is written here in some language other than English. So a very standard way when formatting these data sets is that you have one line per sort of data item. So in this case, we have one line per tweet in this data set. So if I scroll down, you can see that it's one line per tweet, but it's a very, very big line. Get a quick idea of how many there are in each hour, press the capital G button, and there we go. Looks like for some reason it failed to load the whole file. Cut off this right here. I believe this number, so right now I'm on line 53,000, should be about 200,000 per tweets per hour. So let's :Q to get out of that. And what I want to look at next is our map.py file. So cd // there we go, Twitter coronavirus, and then source / map.py. Inside this file, there's this hashtags list. And so these are all of the hashtags that we're looking for inside of tweets. So you can see there's a couple in non-English languages, Korean, Japanese, Chinese, and then a lot of English language hashtags. And what we're going to do is our goal is to count how many times or how many tweets there are that use each of these hashtags. And what you should see is that, say, for files in January, when coronavirus was, nobody knew about it yet, none of these hashtags are really used very much at all. See, like nurse and doctor, hospital, those still be used a little bit. But then come like March timeframe, these explode in popularity and continue being relatively highly used hashtags throughout the rest of 2020. The code down here sort of just opens our zip file, then loops over the zip file, and then opens each file in the folder. So all of these three sets of lines right here are just to get you opening the actual file containing the tweets. And then for each line in the file, do this stuff right here. So the first part is loading from JSON into a Python dictionary. So now tweet right here is a Python dictionary that we can access just like any other Python dictionary. And so tweet at text, this part right here, gives us that location in the dictionary where the actual text of the tweet is. Convert it to lowercase and then search through all the hashtags, seeing which ones actually exist in the tweet. And as we do that, it increments these counters so that it counts how many times the tweet actually appears. Besides the text key in the tweet, there's also a language key. So here it's this counter, it's counting not just the total number of tweets that contain that particular hashtag, but it's also specific for each language. So you can see for English tweets or Korean, Japanese, Chinese, Spanish, whatever other language you want to look at, which ones are talking about coronavirus the most. Any questions about this code, sort of at a high level, what it's doing? Okay. The last thing it does is it outputs a file that contains just a summary of all of the things that have been computed. What you'll have to do as part of this assignment is modify code right here so that it's not only tracking how many tweets exist in each language using these hashtags, but it's also tracking by country instead of by language. So there's a key for the country code that you'll use to determine what country the tweet was sent from. And basically you can copy and paste this code, but instead of using language, you use country code. And then at the end here, instead of outputting just the language, you'll also output the country code. Okay, it looks like our code on the right has finished running. And so if I type ls now, you see that there's this new folder outputs that was created. And so every time you run this map program, it is going to create a new entry in this outputs folder. So ls outputs, and in particular, you'll get one for each file that you run the map program on. If we were to look at this outputs folder, you can see that it's let's switch it over here to the left. You can see that it's a Python dictionary that contains other Python dictionaries. And so this all represents all of the tweets. So in Arabic, there were a total of 2.7 million tweets sent in Arabic. And then let's see, here's the hospital hashtag. So in English, there were 162 tweets that used the hospital hashtag for that particular day. Looking at these JSON files sort of directly like this is kind of cumbersome to do. It's not formatted very nicely. So we'll look at a tool next to more easily format these JSON files. And that's built into Python. It's called json.tool. So Python 3-m json.tool. And then you do outputs this, and it prints that JSON file in a nicely formatted format. And let's see, there we go. So here is that Arabic again. Since none of the hashtags that we're looking at were Arabic, I'm guessing we're not going to see an Arabic in any of these other ones, but here we go. So English, Doctor 281, and then up here, let's find English right there. So out of 22 million, 160 mentioned the word doctor on February 16th. This tool right here is just a generic tool, not specific to this assignment at all, but something that you can find, that you will find useful in your career as you need to look at JSON files to understand what's going on inside of them. Are there any questions about anything I've gone over so far? Okay. So then that's roughly how the mapping works. And you can see that that map took a very long time to generate these output files. Took about 5 minutes. One of the things that I did not do, I didn't directly time it, but in Bash you can use the time command in front of something, say time, and then the program that you're running. So I scroll up to here. I could have said time like this, and it would actually count for me how long it takes. Press Control-C right now to end it. For time, there's these three outputs right here. The real output is the sort of most important. That's the total amount of CPU time the program actually took. User is the amount of time that your code was running these, what we call the user space code, so like actual Python. And then sys is the amount of time that your program was inside the kernel doing those sys calls. So fork is a sys call, but then anytime you're reading or writing to a file, if the kernel is reading or writing to files, then that gets taken up here. But yeah, I guess the takeaway is that this is the one of the real is how much actual wall clock time it used. In order to make these run in parallel, what you'll want to do is again use the fork in bash by putting the ampersand, oops, bigger, the ampersand at the end of the line. And then it will run in parallel and you don't have to worry about it taking too long. So that is the map part. That is the map part of the assignment.
Question.
Yes, go ahead.
Can you go back to the terminal?
Yes.
So if you want this to learn in parallel, then do you still need to like put in more input paths? Like, do you have to pass in more, or like type it out everything? I don't know.
Yeah, it's a great question. So here, this map is going to run on just a single zip file right here, just a single day, but we want it to run on all 365 days of the year. And so in order to do that, you have to specifically call this map function 365 times. That would be a huge pain in the butt, though, to try to copy and paste this 365 times and manually type all of those in. So fortunately, Bash has for loops built in that let you do this. On the, let's quit out over here. So I'm going to create a file called runmaps.sh and add my shebang up here at the top, /bin/bash. And now I'll show the syntax for loops in bash. So for item in 1, 2, 3, 4, 5, do echo $item. Done. So we saw before, last time in class, that you can create variables by doing this export variable equals the contents of the variable. Right now I just typed this in on the down here in the shell on the right. And you can access variables by putting a $sign in front of the name of the variable when you're putting it on the shell. Another way of creating variables is inside of for loops. So here the variable that I'm using is called item, and then this item variable will contain each of these values in this list right here, in this thing that is separated by spaces. So for item in 1, 2, 3, 4, 5, echo item, it'll print out 1, 2, 3, 4, 5 on different lines. Let's go ahead and make that executable, run maps, and do run maps, and we see 1, 2, 3, 4, 5 down here. So this for loop means that we would only have to type out the map command a single time, but we still have to somehow get our list of files into this spot right here. And the way to do that is something called the glob in Python, or sorry, in Bash. In Bash, the star character is called the glob. And what this star character does is it expands into all possible files that can match whatever pattern that you've written out. So here I have these 4 files right here. So if I do echo star, what's going to happen is that star will be replaced by all 4 of these files, and it will put them to the right of echo right here, printing out, passing all 4 of these to the echo command, which then prints out the names of the files. This star is different than the star in regular expressions, which is very confusing. But it's also very useful. So let's see, we have our ls src. So here there are 3 files all ending in .py. I can do echo src/star.py, and the star is like what you can replace it with anything, any set of words, any file that can be put in here, and the previous and the subsequent stuff matches the name of the file, then it'll get output here. So src/star.py gets all of 3 of these files. In this case, src/star would get us the same thing, but if we create a new file in src called, say, like test.sh, so now there's this file that ends in .sh, echo src/star gets us all 4 of the files, including the test.sh. But if we added this top py right here, then this test.sh does not get included. So in order to list all of our zip files, we would want to do something like ls/data fast/Twitter2020, and we don't want to do star all by itself like this, because that'll list not just the zip files, but any other file in that directory, and star.zip will get us just the zip files. So let's count how many of them there are. Piping to wc-l, 366. I guess I forgot last year was a leap year. So in our for loop up here, we change this to /data-fast/Twitter2020/star.zip. And now run maps prints out all of these files. And in order to actually get it to call the run maps function, you change this echo right here to the maps command. You also want it to run in parallel, so you would add that ampersand at the end to make sure they all run in parallel. Are there any questions about that? That was a great question. So the map portion of the MapReduce is generally like the most computationally expensive step. Generally the only part that needs to even consider any sort of parallelization, and it's pretty straightforward to do inside of Bash if you've structured your code so that it operates on a single file at a time. It's just a for loop that looks something like this. The last part is the reduce step, where we have all of these outputs. So again, we said in that outputs folder, it outputs the dictionary of the results, and the reduce step just combines those results together into a single combined result. Since those output files are really, really small, just 1 line each, this step takes no time at all. It's all the computation is dominated by this map step right here. Yeah, under this background tasks, it has some example commands for running this reducing, so that you can sort of get the mechanics of what are the right sort of right commands to accomplish this task. And then under the task is what you're actually supposed to do. So a modification to map.py, like we talked about, you have to create this run maps.sh like we mostly did in class right now. And then there's this visualize.py, which lets you sort of look at the output results, and that's all you have to do. Computation wise, if there's nobody else using the Lambda server, this takes about an hour to run. Took me about an hour to run it all. But since there's a lot of other people using the Lambda server for you all, it'll potentially take significantly longer. So the due date for this assignment is quite a ways away, but you don't want to put it off too long. I recommend getting it completed by 2 weeks from now, so that just to guarantee that you have enough computation time. With that, that's the end of our class today. I'll stick around for a bit for answer any questions that people have. But otherwise, I will see you all on Wednesday.
Thank you.
Thank you.